Hello everyone, I'm Sumit Vishwakarma, Product Manager from Mentor, a Siemens business. I'm here with my co-author TB Galambos. Today we will be presenting a novel variation-aware mixed signal verification methodology to achieve high sigma variation coverage at nanometer design. This is our agenda. We will start with the problem statement. Why we need to do variation-aware verification now. We then talk about the design used for this study and the proposed methodology which uses machine learning approach. Then we discuss the two cases, a comparator latch and the ADC that use the proposed methodology, and finally conclusion.
Thank you, Sumit. So, why do we need to care about variation-aware verification? As you know, next-generation automotive, mobile, and high-performance computing applications demand the use of smaller nanometer-scale SoCs to deliver more functionality and higher performance at much lower power. Process variation is a well-known phenomenon that, due to the smaller physical dimensions, becomes more severe at advanced nodes. Due to the increase in the number of processing phases at these advanced nodes, the number of parameter variation and PVT corners grows exponentially. As lower nodes drive tighter design margins, rising SoC complexity and tighter design margins increase the cost and likelihood of design failure. Verifying a design across PVT variations is an essential step in design verification. Traditionally, it is performed via simulating extreme cases, which are worst-case corners. This is attractive in verifying designs that are characterized by ample margins, such as digital designs, where failures are mostly noticeable in those corner cases, and the cost is reasonable due to the limited number of corners. However, in analog and mixed signal designs, circuit behaviors are more complicated. One has to consider the continuous and nonlinear nature of analog signals. Consequently, checking designs on a limited number of corner simulations may not be sufficient in AMS verification. On the other hand, simulating and checking AMS designs exhaustively in a continuous PVT space is neither scalable nor practical, since the cost of simulation for complex AMS designs can be too expensive.
So if you look at the impact this has had on the SPICE simulation count, we can see this is that we have now got way more PVT corners that we need to simulate. If you look at the typical planar type of process, we might have 5 different process conditions, 3 voltage conditions, 3 temperatures, and so 45 corners total. That's pretty typical. If you look at the typical FinFET type of process, we now have a lot more voltages. This may be 8 voltages, more temperatures, maybe 5 temperatures, and we will have some extraction conditions, maybe 3 of those. So you would end up with 225 corners, and this is 5 times more PVT conditions to cover. And SPICE simulators aren't going that much faster, so we need to get creative. High sigma statistical, though, is where the real explosion is happening. Much larger orders of magnitude type of increase in simulations. If you look at the difference between going from 3 sigma to 4 sigma to 5 sigma to 6 sigma, it's about 2 orders of magnitude per sigma that we add. So just a massive explosion there as we go up to higher sigma statistical, and then with statistical characterization, we are looking at probably about 100 times more simulation in order to produce accurate timing libraries with statistical data. So the problem here is that the brute force for SPICE verification methods, which used to work just fine, These don't work anymore, and we can't deliver the coverage required within production runtimes. We can't actually get the SPICE simulation done to verify chips with any kind of reasonable amount of compute and any kind of reasonable amount of schedule. And when there's poor coverage, there's endless internal engineering debate about whether we have actually simulated enough, whether we simulated the right things, whether we have dealt with uncertainty correctly, whether we even understand the uncertainties, all kind of debates which can lead to a lot more iterations and a lot more time to market. We see also really high CPU and EDA license cost because now we are using tens of thousands of simulators in parallel to solve problems, and this really does linearly increase the cost of verification. And then last, we are seeing longer design schedule and delayed time to market. Even when we do all the simulations that we can, we still have poor coverage for many other reasons. And so we have to make design decisions under uncertainty, and this leads to over-margining.
We will now go over the architecture of the ADC that constitutes our design example. For our client's application, which is an automotive radar, we used a two-step time domain ADC. The motivation for using this architecture is as follows. For a high-resolution ADC at an advanced node, there is a problem with the traditional approach as supply voltage goes down and limits the dynamic range of voltage domain signals. On the other hand, you have the advantage of fast technology because whole technology is biased towards digital design. This has led recently to the proliferation of time domain circuits that profit from the speed of advanced nodes. We have the block schematic of the time domain two-step ADC. In the input stage, the lower left corner of the diagram, we convert the voltage to time domain by using a pulse width modulation technique, so that each sample of the input signal is transformed into time difference between two signal edges. Then, the measuring of the time to digital conversion, TDC, is done in two steps, just like using a measuring tape where you have coarse and fine divisions. The coarse divisions are measured using the counters by counting the number of clock cycles, and the fine divisions are determined by sampling a multi-phase clock. In this case, we use a set of 90 clock phases. The time resolution of this design is somewhere about 5 picoseconds. We use a set of 3 counters fed by clock phases of 120 degrees offset that help us to avoid or at least severely reduce metastability rate by choosing the counter that is least likely to go metastable. Here are the simulation requirements. Our goal is to estimate the influence of the statistical variation of the comparator latch on the ADC's performance, the effective number of bits. We do this in 2 steps. We first want to find the worst corner from the point of view of the comparator latch's offset using an efficient statistical variation method, and then to simulate the full ADC under the worst case condition and to verify the ADC's performance, the effective number of bits. Let us now look into the challenges we faced. With our previous approach, we performed the statistical variation analysis of the latch using brute force Monte Carlo. We ran many simulations and then we found the worst case comparator offset, which is then applied to run the logic simulation by randomizing bits at the edge of the thermometer code. With 4 process corners and supply and temperature variations, we had a total of 16 corners. This approach was not optimal due to the fact that it did not provide a direct measurement of the ADC performance. We had to do an approximate of 3.2 thousand simulations and also use extrapolation to calculate for sigma performance. For the full ADC, in order to get a better performance estimate, we needed to run an estimate of 100 simulations and extrapolate for 3 sigma performance. Pinpointing the sensitive part of our design that has a high impact on the statistical variation of the overall design was not easy. Initially, the digital part of the ADC was modeled in Verilog A. This simulates rather slowly and also does not verify the actual logic circuit that will go into the chip. Therefore, we switched to a mixed mode simulation so that we can run directly the RTL code of our digital team. So we were in need of a solution which can not only provide us with an efficient way of addressing statistical variation, but should work in a mixed signal verification flow.
Let's look at the proposed methodology which uses machine learning based software in conjunction with designer's knowledge. The solution that we came up with, the Solido, uses active learning and had some really nice attributes compared to some of the other algorithmic approaches that we have seen for analog verification. Some of the key attributes of this approach is it covers the entire space, it minimizes the simulations, it targets areas of interest such as worst case PVTs, and for the rest of the space it uses machine learning to make accurate guesses within the specified tolerance. For example, less than 2% or 2 picosecond on a standard cell library delay. The next slide talks in details about this approach. The Solido active learning approach starts by simulating a small amount of the total space, equally spread and covering all main and interaction effects. Once we actually know what a lot of the responses looks like across the space, what we do is we take this data, which is just very small data set relative to the overall verification space, and then build a machine learning model that can very quickly predict outcomes for the rest of the space. The third step, this is where we get into active learning. Here we use the predicted values to decide which cases are interesting and simulate only those. The focus is to get simulation accuracy where it matters. Now that we got this additional simulation data, we can now go back and improve our machine learning models. The next step is model optimization, where we make the rest of the predictions adequately accurate and run more simulation in areas of greatest uncertainty, and continue to go back and improve our machine learning model. Now we enter a self-verification stage where we prove that the areas of interest are covered and that target accuracy is achieved throughout the space. The last step is the knowledge extraction phase, where we can show the designers which variables have the most influence on their design. This really helps with design debugging and manual optimization for improved yield and performance. The proposed solution is a two-phase approach. In the first phase, we apply machine learning based Solido PVT MC verifier tool to extract the worst corner of the comparator let's offset. And in the second phase, we apply the worst corner and simulate the entire ADC with Symphony and Solido in order to measure the ADC's performance, the effective number of bits. Symphony and Variation Designer unified solution provided the right balance for cost and accuracy for our ADC statistical variation. We could perform the variability analysis up to 4 sigma with only 1600 simulations and without doing any extrapolation. Each of these simulations take about half a minute, and so it was well within our simulation cost. Similarly, we can apply the latch worst case to our ADC and perform 3 sigma verification without any extrapolation. This solution gave us good confidence in our simulation results and analysis. For the ADC simulation, each simulation took about half an hour. As we could run 4 jobs in parallel, the 100 simulations could more or less be done overnight.
Let us now look at the simulation of the latch comparator circuit. For simulating the comparator latch, we apply a sine wave input at the required control signals generated by Verilog A blocks, the 5 blocks at the middle of the schematics. On the left top corner, we have the bias circuits with its 2 diode connected transistors. The latch itself is on the right side, connected to load capacitors and the bias resistor. The schematic of the comparator latch. The input signals are applied from the top, feed the gates of 2 PMOS devices. The conductivity of these 2 devices will determine the direction in which the cross-coupled regenerative feedback circuit, the middle of the schematics, will flip. On the 2 sides, left and right, are level 2 digital latches for the positive and negative output signals. Let us now look into the waveforms. The top waveforms, red and green, are the input signals supplied to the latch, modeling a pair of complementary clock phases out of the 90 phases we use for the fine bits. The middle waveform represents the output of the pulse width modulator. Each rising edge of this signal triggers a comparison. The signal is set up so that each consecutive rising edge falls on the input sine wave with a difference of 1 picosecond relative to the position of the previous edge. This is a Vernier-type technique. The bottom waveform is the output of the latch. The number of the cycle in which the output flips determines the offset of the latch.
So we used PVT MC verifier for the statistical analysis for this latch. The tool combines Monte Carlo and PVT analysis to verify your worst case corners at your target sigma. It provides full coverage as if you're running a full Monte Carlo on all your PVTs without running all the simulations. It handles any shape of output, Gaussian or non-Gaussian distribution, and uses machine learning to verify the answer every time.
Here we see the GUI of the PVT-MC verifier tool, and it is showing the probability density histogram for the offset. The tool allows you to specify a target, the max or minimum of the distribution. For our case, the worst case is the highest standard deviation of the offset. The GUI is highlighting the distribution at the very right because this is the way the initial setup was done. However, we are looking to find the widest distribution and not the one that is to the far right or the far left. If the distribution is narrow, it can be digitally corrected. If it is wide and washed out, then we have to investigate further, and it is a red flag for us. The wider the distribution, the higher the number of bubbles we get in the thermometer code, and the lower the performance of the ADC. This is the summary table created by the PVT-MC tool containing the statistical parameters of the distributions for each of the corners. For our goal, we have sorted it by worst standard deviation. As you can see, my worst case is about 7.2 picoseconds. The result here shows the worst case by standard deviation. Here you can see that my standard deviation offset of 7 picoseconds is entirely unacceptable for our case where the LSB of the ADC is about 5 picoseconds. This is one essential information that we have learned from this analysis. The other key observation, looking at the quantile-quantile plot, the bottom plot in the GUI, is that the tail of the distribution is non-Gaussian, which tells us Our previous approach, in which extrapolation is based on the assumption that this is a Gaussian distribution, would have led to inaccurate results. PVTMC verifier built-in sensitivity analysis shows which transistor device is the most sensitive from variation and its impact on the measured output. The graph on the left shows that phase latch P3 has the most impact. From this information, we get more insight into what type of design adjustment to make to improve the performance of the design. Let us now look at the simulation of the full ADC. The simulation of the full ADC is of course a mixed signal one. The pink region contains the analog blocks, pulse width modulator, multiphase PLL that use Verilog A models, and the latches with their bias circuit that are simulated with full transistor schematics. The blue region contains the digital part of the ADC and points to the RTL code of the digital designers. It is followed by a Verilog A DAC on the output, of which we can measure the ADC performance, namely the effective number of bits.
So to simulate the ADC mixed signal design, we use the Mentor's Symphony platform, which is on an average 2x faster than the comparative solutions. It is very flexible and worked with all digital solvers and had lots of powerful debug features. Symphony setup is pretty easy. This is the Symphony command line. Symphony is the name of the binary, and then you specify your digital simulator options, you specify your analog simulator options, and with the config file you specify which blocks you want to simulate in SPICE and which blocks in digital.
Let us have a look at the waveforms from the ADC mixed mode simulation. The top signals, red and green, are the differential inputs to the ADC. In this case, a small amplitude sine wave. The middle waveform are the complementary outputs of the pulse width modulator. It is a bit hard to see both of them here. The bottom waveform is the digital output of the ADC converted to an analog signal by an ideal DAC that we have seen in the simulation setup. In order to keep the simulation time reasonably short, we limit ourselves to a low amplitude sine wave input signal. This will be good enough for analyzing the effect of the comparator latch offset, but of course it does not account for large signal effects that come from the PWM modulator, that anyway in our simulation it is represented by a Verilog A model. The ADC Monte Carlo result for the worst case statistical corner obtained from the latch simulation is shown here. In comparison with our previous approach, this would have required very long brute force simulations to achieve this target sigma. You can see from the linear QQ plot that this is a Gaussian distribution. PVTMC verifier provides real 3 sigma simulation data as compared to previous approach, which was based on extrapolation. This ENOB result would have been significantly less reliable with our previous approach. Just consider this simple calculation. If we run 100 brute force Monte Carlo simulations, we have roughly a chance of 1 into 10 to get a single 3 sigma result within our 100 runs. Let us now conclude our presentation. In summary, with our previous approach, we were not able to do a comprehensive PVT and MC verification coverage at 4 sigma. We had to run many brute force simulations and rely on extrapolation. With the PVTMC verifier and the Symphony unified flow, we were able to perform variation-aware mixed signal verification with orders of magnitude fewer simulations than required for the same level of accuracy by brute force simulation. And we achieved fourth sigma coverage without extrapolation. This methodology helped us identify variations in the design that have the most significant impact on the performance, which in our case is the ADC effective number of bits. And with this information, we could make the necessary adjustments in our design. Without making those design adjustments, there would have been a serious impact on the design yield. In conclusion, the new integrated Symfony platform and Solido variation designer flow has been very useful for us. We were able to achieve variation-aware verification in the context of the mixed signal design of our ADC. Thank you very much for your attention.